Hello, everyone. Thank you very much for joining for my today presentation, and I'm very happy to be here. And thank you for this opportunity to let me present my work. Today, basically, I'm going to present some stuff regarding from data networks to intelligent network, and we are going to discuss together about that what this in network computing promise and what we can do basically. This is the outline for my presentation today. It is, we talk about in-network computing and what hardware basically we needed for having this in-network computing, smart NIC and a smart switch. And then I go through some existing solutions that we have it in the market for in-network computing. The core direct, shield, sharp, in-network monitoring, and bot traffic detection. That this last one is basically my work. And then we discuss about challenges and opportunities of in-network computing. But before I start, I try to introduce a little bit myself. So then I'm researcher in Simula. Simula is a research lab in Oslo in Norway. I have a position there. And so mainly my work there is doing research for in-network computing in general. And then apart from this position, I have another position. I do research in Arctic University of Norway. And there also I do some in-network computing. But there in Arctic University is a bit different. So because there in the University of Tromsø, I try to do machine learning, in-network machine learning, try to have it in the IoT network. But in Simula, I'm more like HPC. And then I've tried to do in-network computing in the HPC cluster. So, so this is a little bit background of myself. This is, and maybe I say that today, somehow my slides that I grab is from the NVIDIA or like Mellanox presentation. Maybe also you see some of this already, these photos. And so we had this passive network already that network devices, they did some, just relay the packets, and they were just passive element inside the network. They didn't do anything. And if we wanted to do some processing, so we need to wait that basically data receive to the endpoints, and then we can do some processing. But we have active network. So active network devices, basically, they can do something more for us, and we can do some processing when the packet is just going through the network. So I call this one active network. So because basically the idea is not new. So we had this idea from 1996, and it's coming from this paper from MIT. That they basically there was this idea they tried to have injecting some program to the network devices to do some processing for us, but at the time there was not basically hardware to do that one, but idea exists. So this was the active networks, but now recently we call it, instead of active network, we call it in-network computing. So I grabbed basically this definition from the Noah Zilberman, and she's very active in network computing. So it is, the definition is basically, it's just very simple. In-network computing is known as in-network computation or net compute. Refers to execution of programs that typically running on the end host. We can do it in the smart NIC, or we can do it in the network devices. So now what we call it just in-network computing instead of active network. But so for doing that one nowadays, we need some hardware, right? So the hardware is basically that now exists, but also maybe today you notice that most of the stuff that I review today is NVIDIA solutions that I discuss. So we have, for example, we have Bluefield DPU, that is a kind of SoC-based smart NIC that we have. We have InnovaFlex, that is an FPGA-based smart NIC. We have switches, for example, like Quantum, that is a smart switch. We have also Connect X5 or Connect X6, that these are kind of like a network chip that we can also upload some tasks to the chip. But with these hardwares that we try to do in network computing, we can have some solutions for each of them. For example, with Bluefield, you can have, so because we have a processing unit, SoC processing unit there, you can do some you can use the ARM cores and do some implementing some security or having NVMe storage access. With the quantum, you can have sharp or shield solution. You need to have the programmable switch, somehow programmable switch quantum. Or with the Connect X, you can also have some other solutions, just like RDMA, core direct, tag matching, GPU direct, or NVMe over fabric. And with the FPGA solution, also you can have some security solution. But this today I try to discuss some of these solutions from NVIDIA. Yeah. So, but well, what is the SmartNIC? So when we see that, okay, the SmartNIC, I try to when I try to start my research on network computing, I say, okay, so we have the term of SmartNIC, but what is exactly the definition of SmartNIC? Because you see the term of a SmartNIC, intelligent NIC, so they are different. So I found this paper that somehow basically answered the questions. First of all, this code I grabbed it from this paper. I put the link of a SmartNIC current trend in research and industry. This code is basically code from the vice president of the Mellanox, now acquired by the NVIDIA. Said that, okay, we have three types of NICs basically. It's a foundational NIC that basically do the very passive and traditional task for NICs, and we have intelligent NIC. This intelligent NIC is a kind of NIC that is not fully programmable, but we can offload some task from the host to the NIC. And we have also DPU or SmartNIC. But also the point here is that we have DPU, data processing unit, and we have a SmartNIC. This was also my question, that what is exactly the difference between the DPU and the SmartNIC? And then I tried to investigate this one. So what is exactly the difference between DPU and SmartNIC? So I couldn't find. So I asked different people that they are like, they have good reputation. I mean, so then we don't have like, yes, what is DPU, what is a SmartNIC? But the only thing is that if we can offload some custom program to the NIC, we can call them just like SmartNIC or DPU. And this is more like a vendor-based something that is common. So then let's say the definition of a SmartNIC is just something that we can offload a customized program to it. An intelligent network is a kind of network that is a kind of NIC that we can do some specific task, is designed for some specific task. It's not general purpose. But in the market, what do we have as a SmartNIC? I categorize them basically. I mean, this is just the two main ones we have based on the processing unit that we have. It is either FPGA based. So for example, like this Innova is basically it's not produced anymore. Innova Flex is FPGA based, and although this is another one, FPGA based solution. For example, for this FPGA, so we have NIC, we have Xilinx FPGA over the Alveo. But when you go for example, to check for this product, you see that they call it accelerator. They don't call it even SmartNIC. But some others they call it SmartNIC. So, but still, there's not like standard terminology for that. So this is FPGA based. Apart from this FPGA, we have also SoC based. SoC based, we have a general CPU on the NIC, and we can do just like whatever you want to do. Is more close like a general CPU. But if I want to compare these two categories, like SoC based and FPGA based, I would say that just like by some simple categories, it's just programmability. So as you see that the FPGA based is more like is more involved, and then the programming of FPGA is more difficult than programming the SoC, because we can use very high level language and we can program the SoC. We can use just like normal C, even Python in the SoC based. So then, but if you want to have a very simple task on FPGA, so there are much more work we need to do for doing this simple task. So programmability of FPGA basically is less than the other one, but flexibility also of the SoC is higher than FPGA based. And regarding the cost, if you want to buy a Bluefield DPU Bluefield 2, you need to pay just like $1,600. But if you want to buy, for example, U250 Algo, it is cost like 7,000. So then the cost of FPGA, like Algo, if I compare here Algo with the DPU Bluefield 2, so you see that the cost of FPGA is much more higher. But you can have a much more efficient solution with the FPGA. But the only problem is that you need to have some expert to basically to program this FPGA. And basically, I'm working on this one. I have, there are two master theses that are working on this. We are going to compare Algo U250 with the DPU Bluefield 2 to see that from the SmartNIC, when we are going to have memory access, which one is faster, and then we try to compare these two, basically these two SmartNICs. And apart from this SmartNIC, so we are going to have also Smart Switch. And as you see that also for this Smart Switch, there are different terminology here. So what is the, we have a Smart Switch, programmable switch, managed switch. So the something, actually I call it here Smart Switch, is the one that we can basically program the data plane. We can access the data plane, and then we can modify the packets there. So then I call that one a Smart Switch. If we wanted to do that, the Smart Switch, so what are the existing solutions for basically for doing that? One way is to having some switches that they allow us to run in some container. We can have some container, and then through the SDK that basically the vendor provide us, we can access to the hardware, and then through that one we can modify the payload, and then we can do a lot of stuff there. But this solution, for example, if I want to give an example, this one SM2100, this is the one of the switch that it allows us to have some container, and then we can run some customer program there. And also it's very high level, you can program it, you can have your own program there. Here, it is very easy to program this solution, but the concept for this solution is that, as you see that there are different layers, and as much as we have different layers, so then we introduce latency by having more layers. And apart from this one, it is basically very vendor specific, because you are working with this SDK, and this SDK is bound to the vendor. So when you have your solution is basically using this SDK. We also basically somehow mapped and forced to use that vendor. And apart from this one, I think that this is also one of the important things, is that this solution is very expensive. It's not very expensive because of the switch itself. The switch itself is not that much expensive. It is expensive because of the SDK. If you want to have the SDK, access to the SDK, you need to purchase quite a certain amount of threshold to the company that give you the SDK. So then, considering that one, having the SDK is quite expensive, makes it very expensive solution to have that one. I also consider that this is not, you don't gain so much regarding the latency, but still you can have some programming, customizing some program in the switch. And apart from that, that solution that you can have SDK, you have also some other switch that you can directly program the ASIC. So as you know, that we can have this ASIC, and then through this standard program like a P4, so you can program this ASIC. And then in each ASIC, so we have hardware, we have different stages, and the parser. So you can, the package that comes, you can introduce some. There are some fast memory, also there are some ILU. You can do some actions there. But so this solution basically is also easy. So because this is very high level language, this also is easy. But the latency for this one is quite low. So the latency is not like previous. But this solution is also is expensive. But the problem for this solution is not any software. The problem for this solution is that basically the switch itself is very expensive. So if you want to have, for example, one of these NVIDIA SM37000 series, it costs just like $300,000 for one of them. So then having one switch programmable P4 programmable switch. Basically, it makes it like yes, it's very expensive to have. And also apart from this one, when you want to have somehow also a bit vendor specific, because you need to have the architecture and you need to also have the compiler from the vendor. Yeah, this is also makes it a bit more yeah, cost like bound to the vendor. So now let's review some existing work regarding this in network computing. One of them actually is just like Core Direct. Core Direct also, as you probably noticed, that most of the work that I present today is mainly regarding MPI and also HPC interconnect. This Core Direct, because we have collective operations and there are like MPI works, and then one of the problem for the MPI is that we try to overlap communication and computation. So, and then there are some efforts to, as much as possible, we try to have high overlap here. This Core Direct is one solution that we can offload some part of this communication to the NIC. But this is the kind of, it's not smart NIC, it's like intelligent. So because we cannot customize it, have a very customized program in the NIC. So we can have this one, where if you want to use the Core Direct, you can even have it, it's not very new basic technology, you can even have it with the ConnectX 2. So it's quite old. Now we are working with ConnectX 7. So with ConnectX 2, you can have this Core Direct. But this is coming from the Mellanox, and this is like coming from industry. But we have also based on this idea, we have also some softwares that is coming from the research. DK Panda Group, I think that you know, from Ohio State University, they have Blues MPI. The idea is exactly the same. They try to offload communication of the MPI process to the NIC, and exactly they use the DPU Bluefield 2. This is also, but that work come from research, but this Core Direct come from the industry. Apart from that one, so we have also this technology Shield. This is for basically if you see that, but this is done inside the switch. If you see that, yeah, there is a failure in the path, so we try to then the switch try to fix it and then find other path. This is something that it works with the InfiniBand switch basically. And the next one that is, I think that is quite interesting, is the technology that is called SHARP. But how it works, so we all know that the MPI processes in the cluster. So we have just one MPI task. We divide the task to different nodes, and we have also collective operations. So there are small operations, and then when we have collective operations, basically they need to exchange the result to have the final result. Collect basically to compute the final result. So if we have one of them in the traditional aggregation, so then the communication and traffic between the nodes, it could be like this one. So there are different ways basically to do that one, but this is one way. So the node 1 and 2, 3, 4, 5, 6, and 7, 8 in this path tree structure, they exchange the intermediate result. And in order to collect, even in the higher level, they exchange the 1 and 3, 2 and 4, they exchange the result. And then in the higher layer, again they exchange the result, and then here everybody have the final result. So then this is the traffic, this is the aggregation that we do. But through a technology that is called SHARP, through the SHARP, we don't need to basically we can reduce the traffic. But how? Inside the switch, if here I'm able to do some small computation here, I don't need to have such traffic. So then basically these nodes 1 and 2, they can send the intermediate result to the A. And then we can send this intermediate result to the upper layer. And inside the switch, we can sum up, for example, if the operation is sum up, we can sum up and find the final result. And this final result can be broadcasted to the nodes. So in this way, we can change the shape of the traffic, and this is much less traffic. But how this, yeah, so then if you wanted to compare, this is the traditional way, and this is the using SHARP technology. But how it works, basically, this chart, it is, yeah, we need, it works with InfiniBand again. It works with the InfiniBand protocol. And as you see that in InfiniBand protocol, basically, we need a subnet manager. So we need a specific node to work, to organize the network. And in order to run it, so we need some small daemon, it's basically SHARP D. We need to run it on the compute nodes. And then we need also to have aggregation manager that is run. It must be run on the subnet manager is a separated node. It must be separated node. And then when we run basically this service, it creates this aggregation basically tree. And the only thing that we need to do, but here we need to use some special MPI from HPC-X package. We cannot run just the normal open MPI because it doesn't work. So then, but this is also free. If you want to use it, just we need to download HPC-X package, and then we use the MPI from the HPC-X package. But this is free based on the software, but it's not free based on the hardware. We need to have at least quantum switch in order to be able to use that one. But for this solution, we don't need to have a specialized NIC. The only things here we need to have a special switch, because this is something that the operation must be done inside the switch. And,
so you said you do not need specialized hardware for the nodes? For the
for the nodes.
But you need to have some
switch.
The software stack, you need to have something that make you allowed to interact with the switch.
Yes, from
the what is the complexity?
No, it is actually, this solution is it is not complex as it shows. Most of these operations, they are just like I would say that automatic, and we don't see it. There is abstraction, but the only point is that here for this one, because I spent some time for this chart and try to see how is it. You need to have quite a good amount of nodes to see the difference. Because, for example, I mean, if you have only 3 or 4 nodes, because it's something that I started to see the difference is when I increase the nodes above 10. If I have less than 10 nodes, when I run SHARP or when I disable SHARP, I don't see any difference. But having more than 10 nodes, 10 compute nodes, then I see that, okay, so I see that I go up to, I didn't go up so many, but to 12 nodes. I tested with 12 nodes. I see that like the latency decreased by just like 2 times compared to the regular MPI. But this is yes, this is but it has also its own problem of this yeah, SHARP. But this is one. But yeah, apart from this one, this is the work that I did that for this network computing. I was thinking that okay, so we have this smart NIC. We can try to do in network monitoring from the smart NIC. So this was I tried to monitor basically the RDMA traffic inside the cluster, and then we had a switch here. This switch was SN4100, and then we had some RDMA traffic, RDMA coming from RoCE protocol, and then I tried to monitor the traffic from the switch. I also read the congestion context from the switch. So in order to monitor the RDMA traffic, I think that we can even use some standard protocol. We don't need to invent something. So use S-flow, because this switch SN2100 support S-flow. So then I enable this one, we can monitor that one. But we need to visualize this monitoring. There is a tool, it is famous in the HPC cluster. It's called PCP. Now, this PCP is basically a tool to monitor the nodes of the HPC cluster, but it doesn't support RoCE. So we wrote a plugin to support monitoring the RDMA RoCE traffic. And after that, so from everywhere in your cluster, you can connect to the SmartNIC and you can visualize your congestion, you can visualize the IP. So this is one thing, but what was the reason behind of this that I implemented inside SmartNIC is that you see that when you have the HPC cluster, so you don't like to because the nodes are usually expensive and you don't like to dedicate a core or something to only for monitoring the stuff. So then it is good that you can have it on the ARM cores that they are light and they are powerful enough for only monitoring the network. So then that was the reason that basically we have these solutions inside the SmartNIC. And this is another work that basically I did, and this one was the collaboration with Noah Zilberman. What was the idea? In the e-commerce website, it seems the majority of traffic that comes to the e-commerce website is from bot traffic. So just I feel like 70% of the traffic I see that coming to Amazon is generated by the bot. So then it's quite a huge amount of traffic is coming from bot. But this traffic, not all of them are like malicious bot. But also from this 70%, the good amount of traffic are malicious bot. But this bot, basically, they can cause us different problems. And then see that, okay, so then the SmartNIC or inside the network, this is the best place that immediately we can detect this bot traffic and we can try to do some smart actions to this traffic. So something that basically we did is that inside the DPU, we try to, through this planter is a P4 based in network machine learning. And we try to basically, when traffic comes to this planter, first we pass the traffic to this planter. And through this planter, we extract the feature of the traffic. Mainly here, we work with two features, the interval of the time for the request of a specific key. The key, I mean, here is just like the product. We suppose that, for example, there is like Amazon or just like e-commerce online shop, and the request coming from the normal or malicious, and they try to ask for some. There is a query I need for some items based on the query, and then the response of the query back to the user. So then, based on the query of the user, so then here we try to see, okay, it's asking for which keys. Which items. So then based on this, we extract that, okay, how often the malicious or the normal user is asking for the key, and for which key, basically based on the popularity of the key, this request comes. So these features we extracted, and then we try to basically distinguish this malicious and normal traffic. And but the point is that this planter is basically only does the inference part inside the SmartNIC. There is not any training or something inside the. So then here we do the inference, and then we try to distinguish also the bot traffic, because bot basically always they don't behave like bot. There are some smart bot that sometimes they behave like intense or aggressive or moderate. So I call them, actually we categorize them in like aggressive or. So then some of them, most of the time, they ask for unpopular items, so they are aggressive. Some of them basically, yeah, they are more moderate, asking for popular items, and then back to turn it on unpopular items. Yeah, they behave basically different. This is some existing work for the network computing that we review. So now the last step, I see that what are the challenges of and opportunities of the network computing. So I was thinking, okay, to see how could be challenging for working of this in network computing. I'll give you by example. So I see that we see that cache table is used a lot for example, for in-memory storage. I see that the hash table with the chain list is not the best data structure for network data access. But imagine that we have a hash table, and these hash tables are different linked lists. And then there is a node remotely, they try to traverse this link and then find the proper key. So then we have it here on the right node, we have a linked list, 3 elements. And then here there is another the remote node try to access and find the proper key there, search it there. So what would be the solutions here to do that one? I would try to do a remote search, right? The first thing that possible to do that one, I try to read the whole 3 elements in one shot by one RDMA read. I can do or read all three elements, but this is basically is under a specific condition because this memory, if I need to read it in one shot, this memory should be consecutive, right? It should have a start. I know exactly the start and I know the end address of the memory, so then I can read it in one shot. This is one possible solution that I did with one RDMA read. Or another solution is that I traverse the linked list and then by 3 RDMA read, I try to read it each item, and then locally when I read it, I see that okay, this is the proper one or no, I can go for the search for the next one. Right? This is another solution. Or I can do another things. I can do some like more fancy stuff. I ask this DPU to do the search for me. And then here I can have just a small process inside the remote DPU. And then I ask from the remote node, I can ask the SmartNIC. So SmartNIC can do and go and search the local memory here through the PCI Express, or it can also be done through the RDMA. And does the search for me, and then find the proper key, find the proper item, and then reply me back the item. So in this way, I don't need to generate any network traffic. So this is it seems that this is a good idea. So I don't need to do that. But basically, when we compare these 3 solutions, it might think that okay, delegating the traversing list onto DP would be the best, but basically this is not the best, and this is somehow it would be the worst case. And the best could be just reading with one RDMA, and then I can just read all of them in one shot. But this is not true that this delegating the traversing list to the DPU it is just always the worst case. It depends on many factors actually. So how long it would be the linked list? What is the size of each items? So it depends on many factors that then I can decide, okay, so it is a good, now if the situation is good to delegate some tasks to the DPU, or so then it depends on the circumstances that I can delegate some tasks to the DPU. So that's why that we have some solutions on demand in network computing solutions. So when the circumstances is good, the situation is good, I can delegate some tasks to the network, but if the situation is not good, so then I come back and I use the traditional basically method. So this in network computing, we need to think basically. So we need to think that exactly what task is proper to offload to the NIC. And we need to think what is the circumstances that it now is good to do the offloading. And also it depends also based on the hardware. So I have this hardware and this hardware is good for this type of task. It is good that I offload it. Otherwise, if I don't that hardware, the hardware is different. So I cannot offload this specific task there. So it depends on the different criteria. But in general, the challenges that we have in network computing is basically, first of all, is the hardware. So the hardware is that there are a lot of resource constraints for this in network computing, especially in the switch. For example, when we have this ASIC, there are limited memory there, and also they are not very flexible to do every operations. We have some limitation there. Also in the SmartNIC, if you have FPGA, also we have some limitation there. So we are also processing unit for the ARM cores. When you offload some tasks to the ARM cores of the DPU, finally you see that you don't gain any performance because the ARM cores there is much more weak than the normal CPU that you can do it in the host. So the first challenge is basically the hardware. So yeah, depending on the NIC or depending on the switch. And another thing challenge is that you introduce basically by working with in network computing, you increase the basically complexity of the solution because you offload some task to the NIC, and then when you wanted to run your solution, so then you have it more component in the system. So then it makes it more basically more complex solution. And another thing is basically the programmability. So then different hardwares, when you wanted to program it to offload some task, there is not there is not like a standard approach, but in reality, there is not a standard approach that works for all of the hardware that you have. Each hardware that you are working, so you need to program it differently. So then you need to deal with different hardwares, different programming. So these are basically the main challenges that that exist for this in network computing. And this is my last slide. Is but what are the opportunities? So we can do different things with this in network. So we can offload some networking, some coordination, aggregation that we gave example. And this is basically in network computing is very good for the security because to be honest, when we talk about this in network computing, especially for the smart NIC, that there is processing unit. I receive this complaint because people they may say this one that okay, so I have some small processing unit on the NIC and it's very cool, but I mean I can have the more powerful CPU on the host, and then I don't bother myself to have some processing unit on the NIC. I can do it like I can change the my CPU to more powerful CPU, and then that's done. But still, for some solutions doing the task in the NIC, it is quite useful, particularly for security, because still you can isolate your host from the network. So then you can do some stuff there. And also for the security, this DPU, apart from this general purpose or other type of processing that they have also some accelerator, and they have accelerator for security, and you can also use those accelerator for accelerating your task. And AI and also caching. This caching, apart from the processing unit, there is a memory there in the network devices. So you can use this one for caching, and you can have multi-layer caching in your network, and so you can accelerate basically. The performance also reducing the latency. These are basically the opportunities that we can have inside the network. That was all. Thank you very much. If you have.
I have two questions. The first one is about standardization. You mean some switches that are vendor specific, some solutions are different architecture specific, Arctic and PCIe. Is there any standardization activity like switching DP or ORAD in the standard network?
I see that there is an effort for standardization, right? But I don't see that anybody in reality they use that one still. That for example, we have this standard and API, for example, that everybody can use it. I didn't see it, but still, when you go and see that different people based on different switch, different NICs, they are basically programming in different way.
My second question is about, I think there is a blur between computation and communication. So what is the purpose of this convergence? So it is like the computing to serve the communication, like the resource management in the warehouse, or communication to serve the computation, like distributed computing?
No, I mean the communication computation. So you need to do, for example, you communicate and then you need to do some computation. But then if you, for example, if you need to wait for communication, that is the point. If you need to wait for communication, then it's just like, it's not good, right? Because you are waiting for the communication. But if I can overlap this one, and I don't need to wait for the communication part, then I can accelerate my solution. This is the point. I mean the communication, I mean that it doesn't need to be serialized. If it can overlap, so then I don't need to wait. That is the point.
So which is the priority, the computation?
No, there is no priority that I do which of them. The point is that the good is to have more overlap, not like we don't serialize that one. So then we wait for the data to come, and then I start do something. I don't say that I need to prioritize something. So the point is that you try to, as much as possible, try to overlap. Then you don't need to wait.
Yeah, so I think I got the point of accelerating points in anomaly detection in software. So could you explain for the point of smart switch compared to the existing switches?
I mean,
sorry.
And yeah, this part, this one, or
yeah, or the earlier when you were expecting
yeah. Actually, the point was that because the regular switch, they do just like relay the packets, and then they don't do any. I cannot have any customized program over the switch. But then I'll say that in order to do some customized program on the switch, I said that there are two ways. One way is to using the SDK that come from the vendor, and this is just I can run some container over the switch, and basically I said that this solution, because there are different layers based on the latency. This is just latency wise is not very good because there are different layers. But then this solution also I said that this solution is a bit expensive, not because of the switch itself, it's because of SDK. Because accessing to this SDK is quite challenging because you need to have a certain amount of purchase to the vendor to provide you the SDK. It is not for free. So then this is one way. And another way is to basically program the switch with directly you can work with the hardware and then we program the ASIC.
Yeah, I think my question then was about what type of customized things you would like to implement.
Here.
Yeah,
here basically one thing that I was something that was my interest. Something is caching. For example, net cache is or switch KV. There are different solutions that they do caching. They do a lot of caching inside the yes. For example, for this in-memory storage that they do, there are a lot of requests that come in for different keys. And then the keys is in the end node in the backend storage. It is in memory of the backend storage. So then here, based on this, it was P4 net cache. It was a P4 solution. Basically, here we can parse. We can see that to which key there is more frequent access for this key, and then I can cache the key here inside the switch. So then for the next request, I can serve it here. But then when I have this type of caching, this solution, then we need to be, I mean, like also this is a bit research, is a cache coherency between here and then the backend data. So we have this cache coherency stuff there. Also, the another thing here is important that we need to, because here the memory is very limited. Then here the solution that we have, we need to exactly pick the very frequent items. So then basically the algorithm to detect the frequent items here is also a challenging. So here we need to see that, okay, which item is challenging or in which level they become popular, then I can cache it here. And then also the eviction algorithm here.
Okay, you put that in an adaptive way based on popularity.
Yes, based on, because also this popularity is changing over time. It's not always fixed. And then, yeah, these are some stuff that you can do. But again, switch, for example, one of them is caching that. See that.
Are there some questions on the bridge?
No. Okay, thank you very much.